For this video, we're going to talk about one of the most common designs in experiments, what we call a randomized complete block design. Our example we're going to be talking about in this video is the boring tree example. So let's say researchers want to determine if the direction affects how thick bark grows of a certain species of tree. So what they did was they took a random sample of 28 trees growing out in the woods, and then 4 borings, hence boring tree example, were taken on each of these 28 trees, one for each direction. So we have our tree, and then we're just going to measure how thick its bark is in each of our 4 directions, north, east, south, and west. And we want to try to see if the direction affects how thick the bark grows on average. So if we were doing a completely randomized design, we'd have that mu north is equal to mu east is equal to mu south is equal to mu west. The problem that we have with these data, though, is that while the trees are assumed to be independent, the 4 measurements that we take from the trees definitely are not. This 72 is going to be dependent on the 66, on the 76, and the 77, because if tree 1 has thick bark, on average, all 4 of these measurements are also likely to be thick. If tree 3 has thin bark in the north, the other 3 measurements are also likely to be thinner than on average. So what do we do? It's kind of similar to our subsampling or nested model designs that we saw in chapters 5 and 7, where each of our experimental units, in this case the trees, are measured multiple times, but the difference is that each of these trees are measured under different circumstances, once per each level of our treatment. So we have one factor in our experiment, the direction that the bark is growing in, and each tree has all 4 different treatments, all 4 levels of our direction factor. Whereas our rat experiment in chapter 7, Ben, the rat, was measured just by Zheng. Charlie, the rat, measured just by Zheng. Dave, the rat, and Eddie, the rat, were measured just by Janet. These rats weren't measured using the different techs, just the same tech per rat. And that's going to be the key difference between a subsampling method and a randomized complete block design. If you change the level that the experimental unit is measured in, then that gives us more information. And so we don't have to consider it just a nested factor anymore. In our tree example, we have 2 sources of explained variation that we've captured in the experiment. First one is the direction that the bark grows in, and that's our variable of interest. And also the trees that were sampled are also going to be a source of explained variation because we're measuring each tree multiple times. So we can include the effect of the first tree, the second tree, all the way down to the last tree in our model. And the direction that the variable is being studied, but the tree is also important to consider. And if there's an important variable to consider, but it's not one that we're interested in, we consider it to be a nuisance variable. And if we have a source of variability that's important to include, but not of interest, we can treat these nuisance variables as a blocking variable under certain circumstances. And the reason why we can do that in this case was because each of those trees was measured under all 4 levels. So we can block by the effect that the tree has. And so since each block, in this case the tree, has all 4 levels of the factor, we call this a complete randomized block design. And in a completely randomized design, the comparisons that we end up making was we'll just take the average bark thickness for all the north measurements and compare it to the average thickness of all of the measurements to see how much the mean of the treatment compares to the overall mean. When we're doing a complete randomized block design, we can do a little bit better. Instead of comparing the average north thickness to the overall average, we'll compare the individual north average to the average of the particular block, or in this case tree, that it came from. So we'll take the first north measurement from tree 1 and compare it to the average of tree 1 overall. And essentially what we're going to do, if I want to estimate how much the bark growing on the north side of a tree affects the thickness, we'll average all of these together. So for instance, for tree number 1, the north bark thickness was 72 millimeters thick. The average was 72.75 for tree 1. So all we'll do is we'll take each of these 4 measurements for the 4 directions and subtract out the average. So we'll subtract 72.75 from all 4 measurements. So the north bark thickness was a little less than a millimeter below average for this tree. The east bark thickness was about 7 millimeters less than the average. The west was about 4 millimeters thicker than average, and the south was about 3 millimeters thicker than average. And these are the ones that we would end up averaging. For all 28 trees, we calculate their averages, subtract the measurements from each of the tree from its average, and then this y bar n will end up being the average of all of these after we remove the effect of the tree. So that way the tree no longer impacts the result of the bark thickness for each one of these measurements. The model that we're going to build for our randomized complete block design, we're going to have T levels for our factor and B different blocks for the trees, is Yij is going to be the response of the ith factor in the jth block. So Yn1 would be the measurement of the first tree in the north direction. That's going to be equal to some grand mean, plus the effect of being in the ith level of the factor. So tau n would be the effect of growing on the north side of the tree. Tau w would be the effect of growing on the west side of the tree. Rho j is going to be the effect of being in the jth block. What effect does being in tree 1 have on your bark thickness? On tree 28 have on the bark thickness? And we can treat these blocking variables as either a fixed effect or a random effect. And for the most part, it's not going to have that much of an influence on our analysis, depending on what type of questions we're trying to answer. And then the last one is going to be the unexplained differences. Knowing the direction that the bark grows in and the tree that it comes from it doesn't mean we're going to get the thickness exactly right. There's always going to be some unexplained variability that's left over, even if we account for everything. And any model that we build is going to have some assumptions. The first one is that the error terms and the blocks are independent of one another. So tree 1 is independent of tree 2, is independent of tree 3, is independent of tree 4. So the overall thickness of tree 1 shouldn't affect or be influenced by the overall thickness of tree 2 or the overall thickness of tree 3. So we want the blocks to be independent of one another. And after we remove the effect of being in that particular tree, so once we take the 72 and subtract out the average, the 77 and subtract out the average, the 66 and subtract out the average, and account for the direction that these barks are growing in, we want the error terms to also be independent once we remove the direction and the effect of the block. So those are our two big assumptions as far as independence goes. We want our errors to be normal with equal spread, and if we're treating these blocks as random effects, we also want them to be normal with mean 0 and equal spread as well. These are our typical assumptions that we've been having in most of the models that we have. Independence across groups and within groups, once you account for the block, and the errors to be normal with constant variance or constant spread. And the last one that we have is we don't want any interaction between the factor and the block, because we can't really measure that. So since we can't measure any interactions, we're going to assume that they don't exist. And the reason why we can't measure the interaction is because each tree is only measured once in that particular direction. If we want to get an estimate of the interaction between the factor and the block, each block needs to be measured multiple times for that particular level. So I'd have to take multiple north thicknesses from tree 1, multiple south thicknesses from tree 3. And with randomized complete block designs, we usually just measure each block once for that particular for that particular level. So we're often going to say there isn't an interaction term between our treatments and our blocks. As far as our model estimates go, we'll say the effect of the block is just going to be the average of that particular block across all of the levels, and then we'll subtract out the mean. So this rho j hat is going to be equal to, we'll average this particular block's measurements across all T treatments. In this case, we'll average the bark thickness across all 4 measurements for this particular tree J, and just subtract out the overall mean from it. So this part will end up being the average for the jth tree, and we'll just subtract the overall mean to see if this tree is above or below average. And then our estimate for the level of the factor is going to end up being, we'll subtract out the block effect from each of the measurements, and then we'll sum them up over all of our blocks. So we'll take the north measurement for tree J, subtract out tree J's average bark thickness. That'll be the effect of north for tree J, and we'll just average all those out. And as it turns out mathematically, it's the same as our tau i's would be without using a randomized complete block design. We'll just average all of the measurements in the ith treatment, so we'll take all of the north measurements and subtract out the overall mean. And then our estimates for the error terms is just going to be the measurement itself. We'll subtract out the effect of being in the, we'll subtract out the average of treatment I, we'll subtract out the average of block J, and then add the mean back in, because we're essentially subtracting out 2 of these the whole time we're doing it. So with a randomized complete block design, we're interested in determining if the factor has an effect on the response. And so our hypotheses are going to be that the effect of the treatments on the response are all equal to 0 if they're all the same. So that means the average north is equal to the average south is equal to the average east, which means then on the influence should just end up being 0. And our alternative is that at least one of these taus is not equal to 0, that maybe the average of the north is different than the average of the other 3. And then our test statistic is going to be the same regardless if the block effect is random or fixed. And this is where it's different between a nested design, where each of the experimental units is measured multiple times under the same level of the factor, versus being measured multiple times where we change the level of the factor. In that, regardless if we treat the effect of the tree as fixed or random, it's still going to be the mean squares of the treatment divided by the mean squares of the error. We're essentially removing the variability caused by the tree. We're extracting that from these different effects, and so we're just going to be left with the trees over the error term. And that's because each tree is measured multiple times. And our error term, and our degrees of freedom for the numerator is going to be our numbers of treatments minus 1. In our case, 4 minus 1 are 3. And it's going to be the number of treatment effects minus 1 times the number of blocks minus 1. And that'll give us a way of finding our p-value for our test statistic to see if the factor has an influence over the response variable we're interested in. So if we compare the two ANOVA tables, one if we were treating this like it was a completely randomized design, and the other one if we're doing it properly as a randomized complete block design, we can see that the degrees of freedom and the sums of squares are the same for the direction. So our factor is going to have the same line regardless of which model we end up using. But what ends up happening is if the blocks have a large influence on the response variable that we see, what's going to happen is we're going to reduce the sums of squares for the error by a lot. Because essentially what we're doing is, if we're not treating it like a randomized complete block design, where we have row J plus our error term, I, J, what ends up happening for our randomized complete block design, if we go from a randomized complete block to a completely randomized design, the error term for a completely randomized design, we'll call that epsilon star, is going to be equal to the effect of the tree plus our unexplained error in our randomized complete block design. If you notice that over here, the effect of the trees plus the unexplained error is exactly equal to what we get over here. If you add these two numbers up, we end up with the error term for our completely randomized design. Also, the degrees of freedom between the blocks plus the error, if you add those up, also work out to be the degrees of freedom for the error. So if the blocks themselves don't explain much of the differences that we see, meaning doing a randomized complete block design isn't beneficial, this term would be small, but you're going to lose some degrees of freedom. So your your mean squared error for a completely randomized design could be smaller than it would be for a randomized complete block design. But most of the time we're doing a randomized complete block design, it's because we believe that the blocks have a large impact on the response variable that we observe. We want to remove the effect that the block has. So while we lose some degrees of freedom, in this example we lose 27 degrees of freedom, so about a quarter of them, what we lose or what we remove from the sums of squares is that much more important. So if we calculate our mean squared error for our completely randomized design, it'd be 29,000 divided by 108, and that would give us about 271, and an overall f-stat of about 0.7, which would not be significant. Whereas if we're looking at a randomized complete block design, we take this 3,201, which is a lot smaller than 29,000, and this 81, which is a fair bit smaller than this 801. But because the trees had such a large effect on what we saw, the error term got a lot smaller. So we go from a mean squared error of 272 to a mean squared error of about 39. And our test statistic becomes that much larger, from 0.7 to about 5, which would be statistically significant. So if we ignore the design of the experiment that we have and just do a completely randomized design, we would not get a statistically significant result and say it doesn't appear to be a difference in the bark thickness based on the direction, where if we do it properly, we would say there is an effect of the direction that the trees grow in. So if we want to follow it up and try to see where the differences lie, we often want to do a treatment comparison. We'll take our different treatment levels, subtract the averages from them, and create a confidence interval. So the standard error is going to be the same, regardless if we're looking at treating the blocks as a random effect or a fixed effect. It's just going to be the mean squared error divided by the number of blocks that we have, because that's how many samples we have in the north or how many samples we have in the east. If there were 28 trees, each of these measurements each one of these means have 28 samples in them, so we'll divide by their sample sizes. And because we're taking the variance of the difference between means, we have to multiply it by 2, because it'll be the variance of the first mean plus the variance of the second mean. We're assuming that they're the same, so the variance of mean 1 plus the variance of mean 2 would just be 2 times the variance of either one of them. So when we're comparing two means, our 95% confidence interval is, we'll take the standard error and our estimate, and we want to find a margin of error. And so our critical value is going to have the degrees of freedom of the MSE here. And that's the degrees of freedom we're going to use for the t to turn our standard error into a margin of error. Let's say instead of just looking at the pairwise comparisons, we want to create a confidence interval for a single mean. I just want to know the average bark thickness on the south side of a tree, μs. This is the situation where our standard error is going to depend on whether we treat the block as a fixed or a random effect. And that's because usually we're not interested in studying just these 28 specific trees. We want to extend the results from these 28 to the entire population of trees. So if we're just looking at a single mean, the effect of the tree doesn't disappear like it would if we were comparing two different means. And so that means if we're treating the blocks as a fixed effect, our standard error is just going to be the MSE over B, what we saw in the previous slide when we're looking at our pairwise comparisons. But if we're treating it as a random effect, we need to take into consideration the variance of the errors and the variance across the trees. So this would be the estimate of the variance for the blocks. And that's going to be the mean squares between the blocks plus t minus 1 times the mean squared errors. And this would end up being the formula that we would use for our standard error for a single mean. Again, it doesn't matter if you're comparing two means, if we were comparing the north versus the south, then you don't have to, it doesn't matter if the effect of the trees is considered to be a random effect or a fixed effect. But if you specifically want to know, on average, how thick is the bark growing on the south side of a tree, you have to consider both the error term and the effect of the block itself.